my lectures and I post them on YouTube. So after that, I send out a video where I have all the topical guide objectives and example questions that are expected in next lecture, as well as the YouTube video link. So you'll get all of that promptly after class. One of the things I find is that everybody has different learning methods. Some people are really good at keeping up with the notes. Some people not so much, right? Some people really like having that second opportunity to go through the notes. I find that providing the video is much better than providing the actual PDF itself. One, because you get to hear what I'm saying and it reinforces the concept. And second, it significantly reduces cheating and all that stuff. So that's why I do it that specific way. Not that I think that you all are cheaters, but I've dealt with them in the past. Okay, so so this course is Advanced Digital Systems. So last year you took 235 Principles of Digital Systems. You learned fundamental concepts of putting digital circuits together, and then you did the lab. So what we're going to do is we're going to build an advanced digital system. So what exactly is an advanced digital system? Any ideas other than what I've kind of thrown up here as concept of a computer? Many of you have them out, many of you had your cell phones out, maybe you have laptops out, maybe you carry things around there. You drove here, right? When you drove here, you have all of these, system on chips that are integrated throughout your car, so that way it monitors brake pressure, brake fluid, how much gas you have in the car. You have all these advanced integrated cars now that can measure how far you are away from a car, how fast you're going towards it, what's the probability of a collision. All of these different systems, you go into healthcare, there's all these different areas where you go and you see all these devices that they're using to measure blood pressure and core temperatures, and being able to use this data to data mine whether or not you want to provide some proactive care. So being able to understand what's going on in an advanced digital system and how it works, all these principles of power consumption, you're laying the actual architecture on top of the organization, and then from there you have compiling code down, and so that's what I'm discussing is this inner circle, this hardware, right? So you learn some principles of hardware and principles of digital systems. So what you're going to be learning is how do you actually align hardware in a computer architecture to be able to execute what's coming from the operating system. So the operating system is basically telling the computer how to operate. How do I make the data flow through a computer? How do I coordinate with the compiler and the assembler? So the difference between the compiler. So you all have written some either C++ or Java or MATLAB code, right? So you write the code, you press compile, magic happens, and then it runs on your computer, right? So what we're going to be learning in this class is the relationship between what, quote unquote, the magic happens when you're getting compiling, which is taking that and turning it into tokens. We're not going to go into actual compiler design, but hardware in an advanced digital system is, you're going to hear me say this term over and over again, compiler-driven encoding of the microengine, meaning that when you actually take some compiled code and then you send it to an assembler, which turns that code into zeros and ones, from there you can then put it through a data path and then it will execute properly. So you send it in, you got the instruction code, we'll go over this in more detail, but then you actually decode the instruction. So you have certain amounts that tell you what the instruction actually is. So for example, if you're adding two numbers, I need to know that I'm actually doing an addition. I need to know what the two numbers are, and I need to know where I'm storing the solution, right? So that's kind of general, basic technical instruction. So all of that gets broken down into zeros and ones. And up here, programmed users, things that you've written. So how many of you have run an app on your phone where the app has run really slow and you've had to uninstall it a couple times and eventually you just get fed up, right? Most of you. So there's like often a barrier sometimes between electrical engineers, and computer scientists, right? Some people really love doing the code. Some people really like designing the hardware. People who are really good at both and understand how they mix together in this advanced digital system become really valuable. And the reason why is if you have that slow app, what they never account for is, all right, well, all this works really well on an emulator, but if I'm actually putting it onto a physical system where they also have to worry about, I have to make phone calls, I have to be able to update Facebook or Snapchat or whatever the young people are using nowadays. That's so the Facebook is for old farts, so I'm officially an old fart now. But you get the idea. It's running all kinds of different systems. And you also have to be, so part of the operating system is you have to be able to ensure that, let's say that you have to call 911 for some reason, right? You have to ensure that all of the other systems have to stop so that 911 call takes priority. That's done in the operating system. So what we're going to be learning about is how you execute that in hardware this semester. Okay. How do you actually say, nope, we're stopping the instruction and we are taking it over. So you're actually going to learn that as well. Okay. So all of that kind of ties into what a computer is. So here is, if you ever end up dealing with Intel again, you'll see this chart many, many, many times. But this is a general trend of transistor sizes. So you start in the 1970s, you have the Intel 4004 processor, and you're only able to fit a certain number, not even a billion transistors onto a chip, right? So we have to be really careful with our design. That's kind of when we're going to learn a little bit of C. So C++ we learned before, that's an object-oriented program, so you learn about classes and how to inheritance and polymorphism. So C actually is more reflective of what's actually physically going on. When you actually code it, you're telling the computer precisely what to do, whereas the compiler and assembler are doing that for you in C++. So you have to be very careful about this when you have only a few. You only put a certain number of transistors on the chip at any given moment, and over time, we're able to increase the chip density. Here you're getting to the Pentium 4 processor, which was in the late 90s, and then eventually you have dual core, quad core processors where you're actually optimizing using parallelism, and we're going to be learning about that towards the end of the course. And so one of the reasons we're able to do that is because what's known as the feature size of a transistor is decreasing. Now we're not really going to get into feature sizes that much in this course, but it is tremendously useful for you to know. And the reason why is because as the feature size decreases, you have to worry about different physical principles, right? So you're really kind of getting into quantum physics and all that stuff. But the key detail for what you're going to be learning in this course is that you have to ensure that the hardware you're designing is reliable. So you have to understand, like, okay, if I'm designing an arithmetic logic unit, I'm going to be coding it in Verilog. That's a programming language you're going to learn this semester. So you get into Verilog, I have to synthesize it down. I'm going to put it onto an FPGA, which is a 386 lab, which is field programmable gate array. So it's Xilinx boards, you plug it in, you put on some code, and it executes it on there for you. Or is it more efficient to do what's known as an application-specific integrated circuit, which is its own computer chip, which does that thing and that thing only, right? So you have to worry about power consumption. You have to worry about performance. We're going to discuss performance a lot. We're going to probably hit it today. If not today, then definitely on Thursday. But you have to worry about all of these different trade-offs. There's no one right solution. Sometimes it's kind of the saying, make it fast, make it cheap, make it good, pick two. Have you heard that? So sometimes you have to worry about different trade-offs, about how, okay, I have to do throughput. I want to make things more reliable and secure. Well, all of those come with trade-offs. When we get into the data path design, we'll be learning about something known as hazards. The faster you send something through a computer, the more you have to worry about whether or not two different elements will get to the location at the same time, and how do you account for that. Right? So power density becomes a big concern. So power consumption is directly proportional to throughput. So do y'all know what throughput is? So throughput is how many instructions do I execute in a given time, right? So if you think about it, it's like if I'm just walking, I consume a certain number of calories, right? But as I'm saying up here, you have to worry about certain type of throughput. I have to worry about going upstairs. If I'm going upstairs, you have to expend a certain amount of energy. If I decide to sprint up the stairs, I'm spending even more. Computers work very similarly. And so what ends up happening is, if you remember that last chart, where the power density, computer chip density, throughput's increasing, well, you end up getting an increase in power consumption. And that's why when you feel the bottom of your laptop, it feels a little warm. So a lot of consideration has to go down into keeping these cool. Otherwise, if we didn't have this, your laptops would probably be as hot as a nuclear reactor, and that would not be good for you. You're carrying around, I don't think that's ideal. You don't want the burnt hands unless you want to be a villain in the next Marvel movie or something. But you get the idea. We have, as engineers, that you're worrying about both the hardware and the software in an advanced digital system, you have to worry about all of these things. All right, so kind of giving you a background overview. So we started out with cathode ray tubes in the 1940s and 50s, and then we had a gentleman named Jack Knapp. We did 235 mode JK flip-flops. Yeah, so that was the gentleman who invented JK flip-flops. He was also the first person to invent an integrated circuit, and that was what he won his Nobel Prize for. So throughout this course, you'll see a lot of, I include industry quotes. Part is to reinforce why are we learning this other than it helps you get a degree. It becomes really helpful to reinforce, okay, this specific thing is useful because specific reason. So in this case, here's how we've kind of evolved over time. This is actually a picture of the first transistor. I can actually zoom in on it. So you can see the gate, source, and drain, and then you have the input here, right? So this is currently on display at Bell Laboratories in New Jersey. It's about yay big, right? Nowadays, they're about 7 nanometers. Can't hold one up with your hand, right? And so this was the first one. They were mounted up there. And then now you're putting several of them, millions or even billions, on a computer chip. So before there's this idea of the tyranny of numbers. That was the term for it. And before you came up with the idea of integrated circuits and what we're going to be learning about in this class, you've heard about how computers used to take up the size of an entire room, right? The reason why is because they thought that every single piece had to be connected to every other piece. So for example, if we were all a computer, we couldn't just run one computer bus through all of you and have different processors, because they didn't understand this. They had to be one going to you, had to be one going. We all had to be interconnected. And that's why these computers got really big, really fast. And then what ended up happening is that we realized, wait, no, we don't have to do that. We can put everything in a data path on one computer chip. And so from there, this is what the advanced research is being done in. For those of you who think that you may want to get a PhD in this area someday, your carbon nanotubes, spintronics. I do a lot of research in quantum computers. DNA computing is kind of using the DNA print. It's not actually taking your blood and putting it in a machine, but it's kind of taking the same, instead of just doing zeros and ones like A, G, C, T, kind of how all of them fit together to form different genomes. It's kind of taking that similar thinking and completely taking a different implementation. So single electron transistors, which is still theoretical, but the whole idea is you're actually taking the spin of where the electron spin is located, and that's the actual logic value, and correlating that to a 0 or 1. So there's all kinds of interesting things that researchers are doing in other areas. So this is my first expert comment. This is from Phil Emma, who's the chief scientist at IBM's research. The irony of Moore's law. So actually, before I say that, how many of you know what Moore's law is? 1 out of 23. Awesome. Okay, so Moore's law. How about, would you like to share what Moore's law is?
Isn't it where the computing power of a chip doubles every 2 years, I believe?
Yes. So it's not an actual physical law. It's just what we've observed engineers are able to accomplish. So the whole idea is that every 2 years, what they were observing at Intel is that they were able to double the number of transistors in a given area every 2 years. So Gordon Moore, he was one of the founders of Intel. He observed this. That's why it's called Moore's law. So here it is saying the irony of Moore's law is that the designers assumed a constant improvement in technology sizes, which is the transistor size, and thus have not properly accounted for their implementation technology in the digital design, hurting architecture improvement. So the computer architecture is part of the advanced digital system. So understanding how all of these tie together, how the coding ties in, how the design of the architecture, and the underlying physical details If you're able to understand that, you'll be incredibly valuable when you graduate. I mean, you're valuable as human beings. So I'm talking about valuable in terms of like your resume and being able to say, oh, I'd like to work for you. If you hire me, you won't regret it. You understand what I'm saying? Okay, so what we're going to be studying in this course is a specific form of architecture called MIPS. So that's microprocessor without interlocking pipeline stages. And when we get into pipelining, it's going to make a lot more sense. So the people who designed MIPS, Patterson and Hennessy, this year they won the Turing Award for this. So the Turing Award is basically it's computing's equivalent of the Nobel Prize. And if you are gonna, so they invented it in 1980, and they finally won the award this year. So to give you perspective, I also came around in 1980, so that's about how long it takes for them to be recognized, right? But so that shows you, like, it's a fundamental concept that really helps you understand how all of these things tie together. But they're still, building upon MIPS now. So even though it's something that was invented in 1980, it still has relevance today. So that's why I'm teaching you the specific architecture. And so if you go back to the syllabus, I tie it in with the specific objectives. So being able to know the architecture of a basic computer system, being able to know the operation of like controls, arithmetic processors, registers, buses, memory hierarchy, that's something we'll learn here in section 5, and cache and virtual memory design. And then knowing the relationship between the hardware and the computer's assembly language instruction set. So I will reinforce enough C for you to be able to understand that. And then likewise, what you're going to be learning, so you all got an email from Cheryl Mendenhall at Cadence Design Systems. So Cadence Design, to give you perspective, so Cadence Design Systems does electronic design automation, so software that actually helps you design computer chips. And they hold a 99% market share in that area. So getting your foot in the door with that company is good. So you're welcome. And what we're doing, I've been working with them to start a pilot program called Internet Learning Services and Digital Badging. And you got 2 courses of Verilog Language Fundamentals and then System Verilog. So the first one is actually how do you actually code in a way that you're able to lay out a computer. So by halfway through the semester, you'll have actually coded up and designed your own CPU. And so the second one is System Verilog, where you're actually going to be focusing on design process. So you don't want to just be, if you're an engineer, you don't want to just like learn everything and do this stuff and just do what you're told. You're probably the type of person who wants to like create and do new stuff, right? So this specific stuff, how the System Verilog design and verification work is how do you take this code and then do proper design fundamentals so that way you can come up with your own stuff in the future. And then the verification is how do you also do that to ensure that you're doing it properly. Intel lost a lot of money until about 2 weeks ago. They had the largest drop in stock in history because they screwed up their divider. They had a floating point error. And we'll learn about floating point arithmetic later in this course. So they had a floating point error, and they had to recall, I want to say, like 20 million computers, and that will destroy public trust in your company really fast. So until Facebook refused to get rid of Alex Jones or whatever happened there, that they had lost the most money, and then until that happened. So the key thing as engineers and computer scientists, so talking about the Alex Jones thing, not in a political way, because I don't really care about your political opinions, but how does public trust tie into your design? Right? So people felt as though that by allowing certain people in there, not designing the algorithms to properly identify who's being harassed online and who wasn't, that the public trust in Facebook had been eroded. So that wasn't just a political issue, that was actually a computer science and computer engineering issue. So how do you tie this stuff into what you're going to do in the future? Verification is a big portion of that. So that's why I included that second one. And what you'll be getting after you complete both of those is a certificate where you can take a digital badge and put it on either a resume or you can put it on a LinkedIn page. And that actually verifies that you have taken this course, you've passed it, and you actually know the specific skills. So you understand C, you understand Verilog, you understand System Verilog. So anybody who's going through like, hey, I want to find somebody who has these specific skills, they would come across you, oh, they took the Cadence course? Oh, right on. Maybe I should give that person more money. So no other university has access to this. And the two courses, I think they're a combined $4,000. If you're in industry, you have to pay $4,000 for them. You get it free. So don't say I never did anything for you. But it's actually tremendously useful. And I've had several former students who have gone on to not either work for Cadence or work in EDA. And this was something that they use the Cadence tools that act. So this is shown to actually help them. So my big philosophy is I want to teach you how to study. I want to teach you how to excel, not just in this class, but in all of your other classes, so that way you get A's, and then empower you so that way you succeed upon graduation. All right, so before we get into the first TGO, I can write down there. You're going to go down. I got to start writing. This is the underlying hardware portion, right? So you have hardware, and then we have the assembler, compiler, we have the operating system, and then we have the code. So this is a very simple version of what we'll eventually be discussing later in this course. And the whole idea is, in the memory element, this is where we're going to store the results of your assembler, right? So the input is from your code, from the operating system, and you get input from the assembler, and the assembler will store it in the instruction memory. So we'll eventually, I don't want to load too much on you today, but eventually we're going to find out that there's two different memories, the instruction memory and the data memory. And that is actually we're trying to prevent a pipelining hazard when we eventually get to high performance computers. So what ends up happening is I develop my own program. It gets compiled and then assembled. And then what's going to happen is it's going to go through the data path. And the data path is actually going to execute it. Right? So I have instruction fetch, I fetch the instruction, I decode it by sending part of it to this controller. The controller figures out which portions of the data path should be on for a specific instruction. Then the data path actually does the work, right? So in this specific case, I would be telling the arithmetic logic unit to add two numbers. I need to tell it from the registers which specific numbers I need to get. I perform the addition, and then the control also tells me where in the memory I store the result. And then from there, if I need to pass it on to the operating system or anything like that, that becomes the output. So is that starting to make sense? So, first, topical guide objective. What is an ISA? You'll hear me say that a lot in this course. Instruction set architecture. We formally define it as a set of assembly language instructions that provides a link between software and hardware. So if you go on Blackboard, you will see something called the MIPS screen sheet, or for those of you who have the course textbook. The very first page is this green page, right? And it has all of these different instructions. Add immediate, load word, store word, you're going to learn about all of these this semester. And so what ends up happening is it correlates, this is what the instruction is in C, and then it says, it's assembled, this is what it will look like in System Verilog. And then what you will learn is, it also has what the specific registers are, what the values are in terms of 0 to 32, because there's 0 to 31 because there's 32 registers. So you'll be able to take the values on the green sheet and then assemble it down to zeros and ones. You would actually know what it actually looks like. So that provides the link between software, C, and then hardware, zeros and ones. And so I want to include another industry quote here. The most amazing achievement of the computer and software industry is its continuing cancellation of the steady and staggering gains by the computer hardware industry. So this was obviously tongue-in-cheek. But Henry Petrosky here is making a really good point about if you're somebody, and so I know some of you are doing computer engineering emphasis, some of you are dual computer engineering, electrical engineering, computer science majors. And so if you're actually able to consider both of these while writing code, this will actually make you, your product that you'll develop also very sellable, right? So given an instruction set, software programmers and hardware engineers work more or less independently. So if you're able to understand both and coordinate them, you can become a program manager. Then you can actually work your way up a company. Like program managers, like you get into industry, you write code, and that's good, right? But in order to actually get to the higher level and become a program manager within a company, you need to be able to understand how all of these pieces work together. All right, so the general idea, so I've talked about the whole idea is we use this to define how the portions of the data path correlate to the code. So you're talking about registers and data transfer mode. So I briefly alluded to this idea of load word and store word. So eventually we're going to talk how do you actually coordinate between the data path and the memory, because it can be really complicated because you have cache memory, which tends to be fast, right? And then you have non-volatile memory, that the RAID disks, which are stored for long periods of time, but the access times are very slow. So you only want to really access those when you absolutely have to. So you want to have to be able to define all of those registers, memory, and I/O. So for Topical Guide Objective 1.2, I've alluded to the difference between these. So it's between assembly language and machine language, right? So assembly language, the idea behind it is that if I have a equals B plus C, my assembly language would be add, and then I have register 1, register 2, and register 3. And then I would have the first register would be my where I'm storing the solution, and the next two would be the actual physical locations of those two values, right? The two values that I want to add. Machine language is then I go, okay, well now I have to put this all into zeros and ones and run it through the data path. So assembly language is formally defined as a symbolic representation of machine instructions, and machine language is a binary representation of the machine instructions. And so actually the example that I was describing here is actually also the one that I have described there, right? So S2, so eventually we'll define what these registers are. Oh, before I do that, when I was in Naval Nuclear Power School, when the professors would start alluding to things that you'd be learning on later but might not make sense, they would draw this big button that just says, I believe. So sometimes you just got to hit the I believe button. So eventually this S1 and S3 and S2 will make sense. But for now, I believe S1 and S2 and S3 is the thing that matters. Right? So, but what that actually is saying is that I need to take the values from registers S1 and S3, add them together in arithmetic logic, and store it in register S2. So then I translate that into a bunch of zeros and ones. So what does this all actually mean? I know this because I've been working on this for years. The first 6 bits are what are sent to the controller, and all zeros indicates add. So then the next 5 indicate, I'll get to your question in a second. 5, 1, 2, 3, 4, 5, 1, 2, 3, right? Okay, so more specifically, and I don't want to jump too much on this, what's known as an R-type instruction. So register type instruction, meaning it actually gets values from the registers and performs some sort of operation on them. We'll eventually define that. So then I have the values here. So this is 16 plus 2 is 18. 16 plus 1 is 17. 16 plus 3 is 19, right? So register 16 is where these S registers start. This one is saved temporary values, right? When I'm running specific programming, these values are saved in local copies before I eventually have to put them into non-volatile. So -2, 2, 1, 3. 16 plus 5. So this is what's known as the shift amount. If you're doing shift operations, we'll eventually do that in a lot more detail. But then this value here basically indicates a specific function. So all of the R types include add, subtract, all this. We'll go into more detail, but then I use these to differentiate code. So basically here, 16, so this is 2, 0 hex is addition. What's your question?
What would be subtraction on the first one?
Subtraction would also be 0, but then this would be 2 hex. So this bit, here, the second to last bit would change. We'll go into that in a lot more detail. I'll believe button. But you get the idea. So this is the function is where you change it. So we'll go, but we will define those eventually. But right now, I just wanted to define the difference between assembly language and machine language. All right. So 1.3 is this big one here. I can promise you that the very first question on the exam will be define and differentiate between computer architecture and computer organization, and give me 3 examples of each. That will be the first question. And the industry quote that I have at the bottom there, I'll allow Dr. Ranganathan, my PhD advisor, to explain why that should be the case. Formally define computer architecture as system attributes of a computer which contribute to its logical execution and are visible to the programmer, meaning that something that I can code can be manipulated, right? So in this case, the instruction set correlates between the software and the hardware, right? And if I'm talking about, if I have specific code, I know that I can access specific registers. That makes it visible to the programmer. So data representation, we just described that in the previous topic of that objective. Also, I/O mechanisms. I need to be able to know where I'm storing everything, where I need to send it to. In a more advanced digital system, even than the one we'll cover in this course, I need to be able to correlate, well, this is the mouse, this is the touch screen. This is what I need to send to the screen itself. This is the keyboard. All of these have different drivers, which then need certain portions of the data path to execute certain instructions. And then, I'll explain the difference here. Memory addressing versus memory technology. Memory addressing is something that is visible to the programmer because I can know how to organize the address so I can specifically state where I need to store something. Whereas the memory technology, when we get to computer organization in a second, is the actual physical detail. So, for example, if I wanted to identify that I wanted to give you something, right? And I am the programmer. And at some point I say, we need to store memory here, right? I would know that memory addressing, I have the first block, I have the second block, and then in the second block, I go to the second one, right? That's memory addressing. No amount of code that I can write will change where you're sitting, right? That's memory technology. So computer organization is the physical details of a computer which are transparent to the programmer. So hardware implementation of an instruction. We'll go into that. Control signals. Where do control signals actually go? So I write code, it's sent to the controller, and the control signals are sent out. You can't manipulate the actual signals themselves with code. You just manipulate which ones are turned on. See the difference there? Memory technology, cache, virtual memory, and then ALU, CPU, and CPU designs, right? Does anybody have any questions about this? All right, I'm going to scroll past the computer architecture portion and go to the story about my PhD advisor. So he had a student interview, Dr. Ranganathan interview at Intel, and this was what's the difference between computer organization and computer architecture was the first interview question. He didn't know the answer. End of interview. So he vowed never again. And I think this is also a really important thing to understand in being able to differentiate what is you can manipulate with code versus what you can't. That's a really important thing to understand in an advanced digital system, which is why the first question I have there is define and differentiate between the two. And that's why I can still say system attributes of a computer that contribute to its logical execution are visible to the programmer because my advisor made me say it many, many times. And so when I interviewed at Intel, they asked me that. They're like, wow, that was a little fast. You see, like, oh, that was straight out of the book. So I came here instead. So this little blurb right here, a very common student error on these exams is that they, instead of saying physical details of a computer that are transparent to the program, people will write invisible. This computer, you see that up there? Is it visible to you? Is it invisible? There's no part of a computer that is invisible. If you say a computer is invisible, you sound crazy. And we're as much as we like it, we're not Hogwarts. Okay? It's transparent, meaning it's there to you. You know it's there, but you can't manipulate it. So it's important. I know that sometimes memorizing word verbatim things is annoying, but sometimes it's really important to understand what words are chosen and why. And in this specific case, the organization that you'll learn is transparent to you. It's there, but you can't manipulate it. You say it's invisible, you are not able to do magic on the machine. Okay. So does anybody have any questions before we move on? If you don't mind, I'm going to, there we go, much better. I want to make sure I know the time so that way I don't go over and that. Okay, so yeah. Transparent is the technical phrase meaning a computing process interfacing function without the user being aware of its presence. So next I want to start defining the actual architecture that we're going to study in this course. So MIPS, microprocessor without interlocked pipe stages, is a general purpose microprocessor architecture designed to be implemented on a single VLSI chip. Now VLSI stands for very large scale integration. So small scale integration is basically what you all did in 235. Anything up to 10 transistors, and then mediums, that's up to 100 transistors. So medium scale transistors are 100 to 1,000. Large scale is 1,000 to 10,000, and then VLSI is anything above 10,000. Okay. So at this point, you all have done small scale and medium scale. So being able to design beyond a small scale, you're putting all, you have your chips together, you just put the wires out on a breadboard and run it, and it works. But how do you actually make it work? As everybody wants a smaller scale chip, but wants it to be able to run a lot faster, that's where being able to do coding like Verilog and System Verilog really comes into play. So 1.5, this is basically the whole goal of what we're doing with these laptops and these cell phones and everything that we're going to be doing in modern computing. The main goal of the design, this is basically of MIPS. What is the main goal objective of MIPS? This is what the question is the high performance in the execution of compiled code. So basically, I want to code or compile my code, get it onto the data path, and run it quickly, right? So this becomes different. So sometimes you have high performance. Other computers demand low power consumption, right? So for those of you who have Fitbits, right? With Fitbit, it would be really annoying if you had to recharge the Fitbit every hour, right? So in some cases, I really need the computer to run with very low power consumption. In other cases, I want it to run, I can plug it in, like I have the laptop plugged in here, and I want it to run fast as possible. It'd be really annoying if I was scrolling through and you had to wait 30 seconds every time I wanted to scroll off the PDF, right? So some cases I want it to be high performance, some cases I want it to be low power. And as I discussed before, those have trade-offs. Okay. And so 1.6, and this is another really important one, the basic philosophy of MIPS is to present an instruction that is a compiler-driven encoding of the microengine. Thus, little or no decoding is needed, and the instructions correlate closely with microcode instructions. So let me read that again for you guys. The basic philosophy of MIPS is to present an instruction set. So that's what was on the MIPS screen sheet. And then I can bring up on Blackboard and can show you that a little later. In fact, I don't have to do that. Yep, MIPS screen sheet. So before I go to that, so this is I know it doesn't look green here, but the whole idea is I have the actual instruction,
And then remember I was telling you that 2 hex is that last 6 digits in the machine code, and then that's the function value, and then the opcode is the first 6 binary digits. So basically this is corresponding to what that actually is. So the RS plus RT source tertiary register, and then RD is destination register. So from those values that correlates. And then down here at the bottom, and eventually you'll learn all of this, is the instruction formats. So I lay them out 32 bits. The opcode, so what I do is I know that the opcode is 0, so that's why I was able to know that 6 zeros is an R-type instruction. Then I had, I think it was 18, 17, and 16 or something like that, right? So RS and RT get added together and are put into the destination register. The shift amount is those 5 bits, and the reason why it's 5 bits is so what's 2 to the 5? 32, exactly right. So 32 bits is a 32-bit data path. So you can, at most, shift it 32 bits. And then the function is these last 6 bits, and so that function corresponds to this value on the green sheet, right? So this instruction set is what we presented in the MIP screen sheet. That is a compiler-driven encoding of the micro engine. So the compiler is going to take the values that are put into the code and then drive it down into zeros and ones. And then we want most of the work to be done by the data path itself. So without going too much into compiler design, which is its own course, but oftentimes some people really want the compiler to run the machine, meaning that they want a lot of stuff done in the compiler. In MIPS, we want the compiler to put everything into zeros and ones, and then we just run it in the data path. And because most of it's going to be stored in registers, and then we want to be able to form those options with the control signals and through the data path, the only decoding that we're doing is those first 6 bits. Those first 6 bits are what go to the controller and then activate the control signals. So the reason why computer architecture is the actual ISA is because I can compile it and it's visible to the programmer. Whereas once those 6 bits are extracted in the instruction decode and it's sent to the actual controller itself, and it produces those signals, that's a physical detail. You see the difference? Yes, no, it's for everybody already. Okay. So that's why little to no decoding is needed. We only want to do a little bit. And the instructions correspond closely to microcode instructions. So you saw an example of that, right? So add, we know that correlates to a very specific opcode. We know specifically the registers that correspond specifically to how we're actually adding it in that code. Okay, so what this whole block here, you'll be able to reread it when you go on the video. But basically what I'm trying to say here is that the reason why we're trying to reduce the complexity is because that improves throughput. Or the objective of MIPS is high performance execution of compiled code, right? So anything that reduces the ability to get the execution started reduces the performance, right? So it's the analogy I would use is if we have a sprint race, right? Performance, ultimately, what goes into the record book is how fast they run the 100-yard dash. But if you also, that's not the way it works on my computer. I turn on the computer, and you also have to account for the person going to the line. They hold up the starter pistol, and if they wait there for like a minute, it's a minute and 10 seconds instead of 10 seconds. And if you're a person who's using that slow app, you don't really care that the actual underlying phone is working fine. You care that so much issue is going on with the app that you're going to believe this app is stupid, right? So that's why we have to worry about this. That's why all of these things become an important consideration. So that's why you want to keep the instruction set as simple as possible. Because if you're correlating it closely to the microcode and the data path, what that means is the more complex your instruction set gets, the more you have to add to your design of your data path. So you want it to be an advanced digital system, but if it gets too advanced, you're adding too much area. And so issue with adding too much area to a computing system? Increase in size, but what ultimately happens when you increase the size? Heat, one thing, power consumption. There we go, that was the answer I was looking for. Ultimately, you want to reduce how much things cost. And if I say, oh, this computer is wonderful, but it's going to cost you each $1 million, how many are you going to buy that? None, right? I walk out broke, but I've made a heck of a machine. So basically, that's kind of what I'm alluding to here with these specific topical guide objectives. So TGO 1.7 is, I've talked about data path a lot, right? And I've alluded to this idea of memory. And so we're breaking down memory into access into two specific types. So registers are fast, right? So if I wanted to, let's say I wanted to time how fast I could collect everybody's homework. Instead of having you guys put up here in the front, I have to walk to everybody, right? So I could collect yours really quickly, right? Because you're in the front. Okay. So it's very efficient. Whereas if I have to go in the back, right? First I got to walk up to everybody, and then in between times, Sydney, for example, wanted to ask a question. They answer the question. By the time I answer the question and get up here, it's taking me a whole minute, right? So different levels of memory hierarchy have different access times. And so registers, I make 32 local registers. So that's what that S1, S2, S3 is. There's 32 of those within the data path itself. They do not, when the moment you turn the computer off, anything that's in there is gone. They're temporary registers. Okay. But they're fast. I don't really care about saving them for long term. In fact, as I swipe out a new program, everything that's in there before is gone. So the fast registers are something that I can interact with fast. I'm the program, let me add these two values and get it to you, right? That's local register. But then I get into cache hierarchy, which means I have to, let's say I need more than 5 variables in my program, right? But my data path only has 5 registers. So what I would do is I would say, I do everything I need with U5. And then what I would do is that you guys would be my cache member. You're what I have for what I need for this specific program. So the way a cache swap works, and we'll learn about this in section 5, is I would say, all right, I'm done with all 5 of you. You all 5 need to get up. You all need to get in here. And then I bring down the next 5 who are going to be doing the next portion of the program. So that's a cache swap. And then if I only have a certain amount, but I even need more, you guys would have a level 2 cache. It would be slower, but I would be able to store more of it. And so that's the trade-off, right? So I need very fast, very expensive, less fast, but I don't need you immediately, even less fast, but so there can be more of you. The faster you make it, the more it costs. That's why the joke I say it's cash money, right? It costs cash. And then I have my non-volatile memory. So I'm in the back now, and this is, you guys would store everything. So I'd tell you everything that they would have done. I'd go, right, answers are 42 and 96, and you guys would store it. And let's say class is dismissed. My non-volatile memory would save it for after the class. And then what would happen is next class starts up. First thing, like, what was that value you need? And you guys would tell me. And then I would pass that all back off to the cache memory. And then say, all right, let's get started with my local registers. So formally defined, data may be operated when it is in a register and only in load store instructions access memory. So the passing that back and forth is load and store. Right? Repeated use of registers in a basic block of code prevents redundant load stores. So the more I have to go to load store and the more I have to do swaps, the longer my program is going to take. So I want to be able to do compiler-driven encoding of the micro engine so I know which specific registers are going to be optimized at a specific time. This allows higher throughput, so faster performance, since more operations directly related to the computation can be performed. So 2, a simplified pipeline structure has a fixed number of pipe stages, and we'll learn about this in a minute, each of the same time length.
Because the stages can be used in varying but related ways, pipeline utilization improves. So let me scroll up past one. Up 2 is going to be the next one. All right, looks like everybody's done writing. All right, so these are, before I go into 1.8, this is the actual kind of just basic data path. And then the 5 definitions are instruction fetch, instruction decode, execution, memory, and write that. So the whole idea is once I compile the code, I put it in the instruction memory. Right? So let's walk through a basic addition. I go through, PC is what's known as program counter. It tells me what specific instruction I'm executing at a given moment, right? So adder tells me I'm going to add because I want to eventually go to the next instruction. We'll go into that in a lot more detail, but for now, just know that there's something that moves on to the next instruction. Instruction fetch. I go here, it's IF/ID, instruction fetch / instruction decode. So the decode takes all that stuff just like we did on the MIP screen sheet, takes 2 register values, sends the value to the controller, and then gets all the values out of the registers and puts them here on this buffer in between them. Next pipe stage. I take these values, I add them in the arithmetic logic unit. So ignore all the branch taking is for when we do comparisons like I greater than or equal to j, for example. I put this value, the result from the arithmetic logic here, unit on here. And then data memory, if I wanted to do load or store, if I wanted to be a longer non-volatile, this is what I would do at this stage. Otherwise, it goes around to this buffer. And then write back is I would write the value back to the register. So now I would write that last value to that specific register for the addition instruction. So that's kind of the general idea. So let's formally define each of these 5 stages. So remember, all of the stages are the same time, and this is going to become incredibly important when we get into pipelining. Instruction fetch is formally defined as a so it gets a compiled MIPS binary machine code instruction from the instruction memory and loads it into the data path. Next, we're going to decode the instructions. That stage is instruction decode. Formally, we state that it decodes the machine instruction and generates the control signals, determines the appropriate registers and memory locations, and the necessary operations to complete the instruction. The next stage is executions / ALU. Most of the executions done in the ALU. Performs the operations dictated by the machine instruction. So that opcode tells me what thing I need to do. Do I need to add? Do I need to subtract? Do I need to shift registers? Do I need, shift bits? There's all kinds of different things that you can do. Do I do and, nor, all kinds of different things. Things that you did in 235. Those comparisons are made there in the ALU in the execution stage. The 4th stage is data memory. If the operation dictates that some information must be stored in memory, it will be done in this stage. So that's load, word, and store. So from 1.7, we saw that everything has to be done in load and store operations, right? So that's where we're going to come in from there. And then write back is when we'd actually be storing the value back into the register, for example, in that add instruction. If the operation dictates that some information must be stored in temporary registers, it will be done at this stage. All right, so I'll let people jot these down for a little bit. So does anybody have any questions about this?
What was the yellow section and the yellow circle down there? Underneath the memory, so you wrote back to?
I'm going to scroll, just so I can address it. I'm going to scroll past execution. Hopefully everybody has that. Okay, so sign extended. That's going to be an I believe button for the moment, but the short version of the answer is that when I have what's known as an immediate instruction. So immediates are anything where I'm taking some numeric value, not something stored in the register. So C equals A plus 5. Okay? So 5 is the immediate value. All of the instructions are stored. One of the reasons why I do the topical guide this for a second and go back and questions like this. You have a fixed instruction number 32, right?
So an immediate type instruction has a 16-bit value to store that number. It's not stored in a register, it's actually stored in the instruction itself. But if I'm putting it to the arithmetic logic unit, I need to add on 16 more bits. So if it's a negative number, I add in all ones, if it's 2's complement, if it's a positive number, it's all zeros. So that yellow value, that sign extension, I'm taking a 16-bit value and I take out the same value that's 32 bits. So I can send it to the arithmetic logic. Other important values, reasons for doing that, to be determined.
Any other questions? I don't know, another minute or so for people to write things down. Again, since it's the first day, I want to emphasize I do post the videos, so don't feel bad if you don't get everything. Yes. I will post it within 10 minutes of being concluded. Yeah, 10 minutes of me getting back up to my office and then posting. But it is actually recording right now. And so what I do is I will upload it to YouTube, and then I send out Blackboard. I tell all my friends on Facebook. They're like, I'm not doing this homework. I'm not in the class. Yeah. And you can be as bored as my students. No, I will post it. I post it on Blackboard, and just like all the other things, it sends out the automatic mail, so you'll get that. And depending on whether or not somebody bothers me, it's usually within 10 to 20 minutes of after lecture. Yes?
As far as recording, is it in step with what you're showing us here, or is it?
Oh yeah, it's recording. It's recording the screen, and it's recording what I'm saying. Yeah. So it's literally, yeah, the lecture. Okay, cool. Any other questions? No, I mean it's a fair question. Yes.
We have a TGO due Wednesday?
Yes, every day, every lecture, and they will be returned the following one. So the logical follow-up question is the one that's done the day before the test. Obviously, that's not going to be on the exam. But I also like to tell my students that usually my exam reviews last 5 minutes. I say, what do you think will be on the exam? And you guys are usually pretty good about saying exactly what's going to be on it. So, all right. So that's what's there for now. All right. So another thing that's important is differentiating between RISC and CISC. So RISC is reduced instruction set computer, and CISC is complex instruction set computer. Now, there's pros and cons for each. One of the reasons that I'm doing RISC is because this is a new concept to you, and so throwing a complete CISC data path at you would overwhelm everybody. But I do want you to understand the fundamental differences, and as you move on in your careers, CISC is something that you can understand in more detail. Reduced instruction computers have fixed instruction lengths. So in this case, our data path is 32 bits. So everything is it's simpler, limited number of addressing modes and instruction types, for example, load word, store word, registers. It can be executed in a single cycle. Therefore, we can have higher clock frequencies. So in short, what ends up happening is I can do it in one of two ways. So this single cycle, so I have one clock cycle, right? So but between the time I have a rising clock signal and the next rising clock signal, I will have completed the entire addition, right? Or I can have very small clock cycles, and then I can do fetch, decode, execute, memory, and write back. And then what we're going to discover is that because that's done and we have buffers, you can actually do the next instruction cycle fetch in the next cycle there. So that's pipelining versus single cycle. So comparing this to complex instruction set computers, or CISC, many instructions, and oftentimes there's several hundred. So in MIPS, there's 64, but you can actually exit everything that we're going to do. You're going to learn 16 of them, right? You're going to actually 16 instructions in there is Turing complete. several hundreds, which is why it'd be a bad idea to just throw all these at you at once. Variable instruction length, so sometimes it can be, if you can execute it in 32. If you want to do it for insist, so in RISC, if I wanted to add 5 numbers, I would add the first 2 stored in a temporary register, then add the 3rd one to that previous result, and add the 4th one, and add the 5th one. If I want to do CISC, and for some reason I thought that adding 5 numbers is actually really important, I would actually put that as part of the data path and allow it to add 5 numbers at once. So you would actually have its own specific arithmetic logic unit, which adds higher performance, but also would add cost. So it ultimately depends on what the customer wants. And an instruction can take many cycles to execute for that specific reason, because you got to identify what the instruction is, what portion of the data path you want to use, all that. I'm sorry, I thought I saw a hand up for a second. Also, as everyone's jotting it down, I'll reiterate one of my philosophies. It is your right and privilege to ask questions, so please don't feel shy about it. Okay. All right, so TGO 1.10 is something that's actually really good for not just this class, but for the rest of your careers. In order to design an effective ISA here, but you can say effective anything you want, right? The following design principles are used. Simplicity favors regularity. If you are doing something, addition, subtraction, multiplication, division, and your data path, or whatever it is that you're designing, does that often, that's one of the main functions of the design. It's like it's over. But if you're doing that and it's one of the important things that you want to do, you don't want to make that thing complex, right? You want it to be simple. So simplicity favors regularity. You want the things that are done regularly to be done simply. Second, smaller is faster. It's like anything else. If you're running a 100-meter dash versus 5 miles, which one is going to take you faster? 100-meter dash, right? So it's anything else. Like if you're going through switches and calculations through the fewer number of transistors, the fewer number of out register elements, the fewer number of instructions that you execute, it's going to run faster, right? That just makes sense. So make the common case fast. You want to make it simple, you want it to run fast. So the thing you want to emphasize is what are the things that I'm doing often as opposed to the things that I'm doing every once in a while. So kind of alluding to this problem of the app that takes a long time and you get frustrated and delete it. Oftentimes they forget about not updating Apple. They forget that this little extra thing that they spend a lot of time coding that consumes a lot of time and energy doesn't really do much. When you come see me in my office, sometimes you might, and engineers do this all the time. I still do this all the time. At least that's what my fiance tells me. You focus on something that's small and you're like, oh, I really want to solve this. I really want to solve it. But then I'll point to the side of my office that says better is the enemy of good enough. Okay. If you do all these extra things, but your program or your chip doesn't do the thing that a customer asked for, did you actually deliver? No. So trying to make things super awesome, first focus on making the common case fast, make the thing that's being done regularly simple. And ultimately, this last one is the most important. Good design requires good compromise. If you can explain why you've made a design compromise to your customer, that is a huge thing. That a lot of times you'll find you talk to employers, like, what's the thing that you wish students had? The ability to get in front of customers and tell them why it is what they did. You'd be shocked how few engineers can actually do that. So being able to actually say, all right, this is why I'm doing it. We had to trade off this for specific performance, but ultimately it reduces costs, and you have a specific cost metric that you really want to get us to. By doing this reduction, we're still meeting your performance goals, but it's not faster because we also want to meet your cost goals. So
you've articulated that you care about what they're doing, you incorporate that into your design process, and you met all their objectives, and you feel much more comfortable and say, sure, here's the money. So that becomes really important. All right, we still got 7 minutes. Good. So getting into, we'll get into performance. So the first thing I want to talk about is, remember the philosophy of MIPS. Let's see if anybody remembers. What was the basic philosophy of MIPS? It was 1 point.
High performance.
Yeah, high performance execution of compiled code, right? The first thing I'll learn about is what is actual high performance before we get into more details about what is actual compiled code. So what I found is in dealing with performance type questions, people get really confused about what specific terms actually mean and how to actually apply that into developing an equation. So if you remember sophomore or junior year in high school, you did stoichiometry and chemistry, and you had to lay out all of the, you're like, oh no, not again. I promise I won't teach chemistry, but one of the things that is good though is that principle of laying out the units in a way that they cancel out and multiply so you can keep everything straight. And so what I'm doing here is I'm teaching you how to actually lay out performance equations in the same way. So it's not like you're going to get an exact word problem that'll tell you, all right, this is the throughput, this is the execution, and then you can just follow it. That's not the way you're going to get everything. Sometimes you're going to run a computer and you're going to get a bunch of metrics that come from the operating system analysis. And you need to be able to take those and figure out what it is based on what your customer is asking for and produce a solution. So the first thing I think is let's break down the terms so that way you can understand then how to put those into the equation. So execution time is seconds per instruction. It's the total time required for a computer to complete a task. So the throughput is the number of tasks completed per unit time. So if you think about those two definitions, they're just the inverse of each other, right? So if I say a real simple type question, my execution time is 1 nanosecond, what's my throughput? You would just go 1 over 1 nanosecond, right? And then that's why performance is 1 over execution time. Any questions on that so far? All right, so example question 1.1. So in the homework assignments, all of the TGOs and example questions that are covered in class are what are due. Next. Example 1.1, if a computer A runs a program in 10 seconds and computer B runs the same program in 15 seconds, state the improvement in performance of A over B, right? So that's where these are terms that are commonly used in industry, which is why it's important to be able to kind of work through what is apparently a simple problem to make sure you understand the terms. So these 10 seconds runs the program, and the 15 seconds. So that's the execution time. So the performance is 1 over the execution time. So oftentimes you'll calculate the execution time, and you have to tell the customer, or so you can assume when you do the test that I'm the customer, and you're trying to justify to me why a computer-specific program or specific data advanced system has high performance. In this case, one of them is running in 15 seconds, and one of them is running in 10 seconds. So performance A over performance B is equal to execution B over execution A. That just becomes 15 seconds over 10 seconds. The improvement in performance is a scalar value of 1.5. And so if we did this the opposite, let's say I did 10 over 15, right? And that comes out to 2/3. But what's actually happening is that's execution A over execution B, right? So that means it's just performance B over performance A, right? Then that just means that the performance of B is 2/3 as good as the performance of A. So, and we'll see when we'll work questions. I'm going to do one more topical guide objective, and then we'll do through 1.13, and then we'll conclude lecture.
So next, you don't just have a random instruction. Sometimes different data paths do different portions of the instruction faster. Some of them decode the instruction faster. Some of them do the execution faster. You get the idea? So clock cycle time is how fast the clock is actually running. The time for one cycle generated by the processor. Whereas the clock rate is how many cycles are generated per given time. So 1 gigahertz is the clock rate when you can generate 1 billion cycles per second. And therefore, clock rate is 1 over cycle time. And then CPI is clock cycles per instruction. So if I have a number of specific cycles it takes for me to execute an addition or multiplication, or in many of these problems, we'll just have instruction type A, instruction type B, because that's often what you'll get from a customer. And then to calculate CPU execution time, there's several different ways to do this. So setting up the units, clock cycles times cycle time. So if you think about it, cycles times seconds over cycles, right? So going back to your stoichiometry, those cancel out, and that gives you execution time. Likewise, if you do it the other way, divide them, clock rate divided by cycle time, that'll also come out to seconds. And then you have instructions times CPI. So that's cycles per instruction, right? Times instruction. Those cancel out. And then you have cycle time, which is seconds per cycle. And those cancel out. And then likewise here, divided by clock rate gives you the same thing. So example 1.1 and TGOs 1.1 through 1.13 will be due at the beginning of next lecture. I will upload this up when I get back to my office, and we'll send out the video as well. Does anybody have any questions before I conclude lecture? Awesome. All right, best of luck to you guys this semester, and I'll see you on Thursday.